Hey guys, this is Gas Laws Part 2. Please follow along with the notes and let me know after this if you guys have any questions. So here's your question of the day. It says, what is the mass of 3 liters of hydrogen gas at standard temperature and pressure? So just as a hint, you're going to be using the ideal gas law, which is PV equals nRT. So if you guys will pause this video and try and solve that. Okay, so here's how you solve this. I'm using my ideal gas law, PV equals nRT. I'm looking for mass, which means I'm going to need to find my moles. So I'm going to say PV over RT will give me moles, and then I'll need to convert to grams later on. So STP means standard temperature and pressure. Standard pressure is 1 atm. Volume is given to us at 3 liters. We're going to put that over R. R for atmospheres is 0.0821. That's just a constant that you'll need to know. And temperature at STP, if it's in Kelvin, it's just 273 Kelvin. So that's what your mass should look like. When you solve that, you should get 0.1339 moles. Since this is hydrogen, and it's actually H2, hydrogen gas, I would need to multiply by my molar mass to get grams. So I'm gonna multiply, it's like 1.008 times 2, so it's close to this number. Whenever you multiply those two together, you should get 0.268 grams of hydrogen gas. So that is your answer for the question of the day. All right, so we're continuing on talking about some of the other gas laws. First, we have Dalton's law of partial pressure. In chemistry and physics, Dalton's law, which is called Dalton's law of partial pressures, states that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressures of the individual gases. So that means each gas contributes part of the total pressure, which is indicated by this equation. It says P total equals pressure 1 plus pressure 2 plus pressure 3, and so on. You basically just add up your pressures to get a total. The container on the right contains 4 gases. We have argon, oxygen, nitrogen, and carbon dioxide. So just to put it simply, the total pressure inside the container is equal to the sum of each of the pressures of the individual gases. If the total pressure inside is 786, that means each gas contributes to that total number. If we started to remove gas one at a time, the pressure is going to decrease, obviously. Eventually, there is no gas left in the container. The pressure inside would be 0. This seems like common sense, so let's talk about the volume. The container has a total volume of 1 liter. Does each gas contribute part of the total volume? No, because gases are in constant random, really fast motion, so they're moving throughout the whole container. Each gas has its own volume of 1 liter. Additionally, since the amount of gas is proportional to the pressure, Dalton's law can also be written in T, P-A-P-T. So I have moles of the gas over moles of the total, and then I have pressure and then partial pressure, and then I have that over my total pressure. This means that if argon contributed 20% of the total pressure, then 20% of the total number of moles would also be argon. So those are direct. From our previous discussions, we know that the N is your mole fraction of a gas, Na over Nt. It represents the fraction of the total number of moles of gas that's contributed. In this case, if argon contributed 20% of the total pressure, the calculation above would produce a value of 0.2, which means the same thing as 20%. All right, so let's look at a practice problem. A 1 liter sample of dry air at 25 degrees Celsius and 786 mmHg contains 0.925 grams of nitrogen, plus some other gases, including oxygen, argon, and CO2. What's the partial pressure in mmHg of the nitrogen in the air? What's the mole fraction or mole percent of nitrogen in the mixture? What's the total number of moles in the container? So lots of questions. We're going to do this one step at a time. First, using the ideal gas law, we can calculate the pressure of nitrogen, assuming we just use the moles of nitrogen. Remember that each gas has a volume of 1 liter since they all move throughout the container. So first thing I want to do is figure out how many moles of nitrogen I have. So if I have 0.925 grams of nitrogen, which this is nitrogen gas, so it's N2, all I need to do is divide by the molar mass of N2, which is about 28. When I divide those two, you should get something like 0.033. This is going to be moles of N2. Okay, so now I can use my ideal gas equation that looks like this, and I can just plug in numbers. Okay, so I don't know the pressure of nitrogen right now. That's what I'm trying to find. So pressure equals nRT over volume. N is 0.033. R is 0.0821 if I'm using, let me erase that. If I'm using ATM. And then we also know temperature in Kelvin, 298. So I can multiply across the top. And then I am going to need to divide by 1 liter, which is my volume. When you do that, you should get a pressure of 0.808. This is in ATM because my R constant was for ATM. Okay, let's see what to do next. So this is known as the partial pressure of nitrogen. So I'm going to put P in. It also represents the amount of total pressure contributed by nitrogen. Since the fraction of the pressure contributed by nitrogen is the same as the mole fraction, we can say this. So N of nitrogen over N total equals pressure of nitrogen over P total. So now I'm just going to plug in numbers to that equation. I have the moles of nitrogen, which was 0.0330. That's what we calculated a few minutes ago when we were up here. So that's where I got that. That's moles. We can put that over the total moles, which we have no idea what that is, so I'm going to leave that blank. We can say our total pressure of nitrogen, which is what we just found, so 0.808 pressure, over the total pressure, which is given to you in the question. So let me go back one. In the question it says 786 mmHg, so 786 mmHg. But this 808 is ATM, so I need this to be ATM. So I can just divide it by 760, in which case I would get 1.034 ATM. All right, from here I can solve for NT. All I need to do is cross multiply and divide to solve for that. And when you do that, you should get 0.0423, and this is your total amount of moles of all the gas. Okay, we can also find RMS speed of gas molecules. Gas molecules move rapidly and randomly throughout the volume of the container they occupy. When examining all of the molecules of a particular gas individually, we can see that not all the molecules of a particular gas at a given temperature move exactly at the same speed. This means that each molecule has slightly different kinetic energy. So when we examine a gas at a particular temperature, we have to discuss the average kinetic energy. We know, according to the kinetic molecular theory, that kinetic energy of a gas is directly proportional to its temperature. So energy goes up as temperature goes up, or energy goes down as temperature goes down. So it's going to be the same as the speed. By manipulating various equations for kinetic energy, we come up with this equation that's in pink. So the weird looking thing that looks like a U, that's known as the root mean square, so RMS, speed of a molecule. It represents a statistical average speed of all the gas molecules of a particular gas in a container. It's primarily dependent on two things, the molar mass and its temperature. This makes sense because the larger molecules are going to move slower, but the higher temperature, they're going to move faster. So there's kind of a picture of what that looks like. So let's look at a practice problem. It says, what's the speed of a nitrogen molecule in 10-liter container at a pressure of 2.55 atm and 35 degrees Celsius? How do volume and pressure affect? So they don't affect anything. The only thing that affects speed is temperature and the molar mass of the gas. However, the SI metric unit for speed is going to be meters per second. So your answer will be in meters per second. A different R value is going to be used this time. It's going to be 8.314 joules per mole times Kelvin. This is written down there for you so you can kind of see it. But therefore, when the square root of the entire equation is taken out, that's why we'll have meters per second for the speed. All right. Also, one thing to note, that last bullet point, if this value is used, kilograms per mole is what we need to use for molar mass. So normally it's grams per mole, so just make sure you convert that by moving the decimal 3 places to the left. So now I can plug in numbers. The first thing I'm wanting to plug in, let me go back to my equation here, is 3. So it's the square root of 3 times R, which you said was 8.314, times temperature, which is 308. Again, that's in Kelvin, so I just added 273 to that temperature. All of that is going to be over my molar mass, which this is nitrogen gas, N2. So the mass of N2 was around 28. We need to move my decimal 3 places because it needs to be in kilograms per mole. So I'm going to put 0.028. All right, so go ahead and do that math on your own. If you need to pause the video, you can, but you should get about 524 meters per second. Don't forget that this is a diatomic element. It's N2, so that's why my mass was 28 instead of 14. Next, we have Graham's law of effusion. Given that we now know how to calculate the speed of a gas, we can compare the speed of two gases moving through one another. A process involving movement of gas particles similar to diffusion is effusion, the escape of gas molecules through a tiny hole, such as a pinhole in a balloon, into a vacuum. If a mixture of gases is placed in a container with porous walls, the gases effuse through the small opening in the walls. The larger gases pass through small openings more rapidly than heavier ones. Okay, so a balloon filled with air remains full overnight. A balloon filled with helium partially deflates because of smaller light helium atoms effuse through small holes in the rubber, and that happens much more readily than the heavier molecules of nitrogen and oxygen that are found in air. So that's why helium balloons, they're going to lose air very, very quickly because those little atoms are going to be able to escape through the rubber. By comparing the speed equations of two gas molecules, we can obtain the following equation, known as Graham's law of effusion. So that's there in pink for you. Where it says mm, that's just going to be your molar mass of the gas. When using this equation, the assumption is that gas 2 travels faster than gas 1, or that gas 1 is just heavier than gas 2. So that way the rate fraction is always a number that's larger than 1. If it takes 52 seconds for 0.1 moles of iodine vapor to effuse from an opening in a vessel, then how long would it take 0.1 moles of hydrogen to effuse under the same conditions? So we have to calculate the rate of the two gases, which is given to me in this equation. It's like a fraction, okay? So I have the square root of my mass of iodine, which is I2. So that's where that 254 came from. and I have the mass of 2 hydrogen, which is about 2. That's rounded a little bit. So I can go ahead and get the square root of that. When you do that, you should get 11.27 over 1. If the iodine takes 52 seconds, do we multiply or divide the time by the rate to obtain the time it takes for hydrogen to effuse? Since the hydrogen is faster, we need to divide. So 52 seconds, which is from the problem, divided by the rate of iodine, 11.27, gives us 4.61 seconds for H2 to effuse. Okay. Density of gas in Dumas's law. In the early 19th century, Jean-Baptiste Dumas, a distinguished French chemist, created a relatively simple method for determining the molecular mass of a volatile liquid, meaning that's something that just evaporates really quickly. It's not super stable. By vaporizing a volatile liquid into a gas, one can easily measure the density of the gas if isolated in a fixed volume container. So we already know that density is just mass over volume. If you look at the ideal gas law, you have PV over NT equals R, or just PV equals nRT. Again, N is equal to moles, but that's also equal to your mass over the molar mass. We know that from the mole map, so here we go. To get this equation, you can substitute molar mass for N, which looks just like that below. If you multiply both sides by M, you get the next bullet point. If you divide both sides by V, you get the next bullet point. So basically what's happening is molar mass and volume are switching spots. Since mass over volume is density, we can just take out that equation and say molar mass times pressure equals density times R times T. Standard Dumas method setup involves a small amount of volatile liquid in a rigid fixed flask. The liquid is then heated using a water bath so that we know the temperature. A small pinhole is going to be placed in aluminum foil to help some vapor escape. When the last bit of liquid vaporizes, the flask is removed from the heat and cooled so that the vapor is going to be trapped inside the flask. Using the temperature of the vapor, which is the same as the water bath, the pressure of the air, which is the same as the pressure inside the flask, the mass of the vapor, which is now trapped inside, and the volume of the flask, the molar mass substance can be determined using this formula. So if we have 4 of these things, we can figure out the molar mass of a compound. So here's kind of what that setup looks like. We may do one of these in class, I'm just not sure yet. Okay, so here's my equation again. It's more useful at times than the traditional gas laws equations because it has density in it, which is something that we can easily measure in the lab. So let's look at a sample problem. It says, what is the density of elemental oxygen in grams per liter at 25 Celsius and 0.85 atm? So we're going to use Dumas's law. Remember that elemental oxygen is just O2. That's how it's found in the atmosphere. So its mass, 15.999, would need to be multiplied by 2 to get 32. Also remember that you're converting temperature to Kelvin. So my temperature is 298 Kelvin. I'm going to go ahead and write down my other units. Okay. Molar mass was 32. So I need to plug in my numbers. So molar mass, I'm actually going to rearrange my equation first because I'm looking for density. So molar mass times pressure over RT will give me density. Okay, molar mass is 32. Multiply that by your pressure, which is 0.85 atm. That's going to be over R, which this is atm, so 0.0821, times your temperature, which is 298. So when you solve that, you should get 1.11. This is density, so my unit is grams per liter. Okay, collecting gas over water. Sometimes gas is produced in a chemical reaction. The gas is bubbled through water and collected in a separate tube or container above the water. The total pressure inside the container, though, is not just the gas. Some water has evaporated and is starting to add to the pressure of the gas. So if you look, there's like a beaker of some sort in the water bath. The top of the container contains the gas produced from the reaction, but also from the water vapor. So we have to figure that out. The total pressure inside the container then is the pressure of the gas and the pressure of the water vapor that evaporated. So let's look at a practice problem. Oxygen can be prepared from heating potassium chlorate. How many moles of oxygen would be obtained from 1.3 grams of potassium chlorate if the oxygen is collected at 23 degrees Celsius, which we will add 273 to in a minute. The total pressure is 745 mmHg. What volume would the oxygen occupy? We have to do the same thing we always do. First thing we need to do is write the chemical reaction. So I'm actually going to turn my screen here so I have a little bit more room. So I have 2KClO3. I'm just copying this down. Okay, so the first thing I need to do is convert grams of KClO3 into moles by dividing by the molar mass of this whole thing. So the molar mass I already calculated is here. When I divide those, I get 0.0106, and this is moles of KClO3. So we will need that in just a minute. Now I need to do some stoichiometry and set up a ratio because I need to figure out how many moles of oxygen I have. Okay, so I know I have 0.0106 moles here, which means I just bring down my coefficient, 2 moles, 3 moles. Now I can just cross multiply and divide. I'm going to do 0.0106 times 3, get an answer. Whatever that answer is, you're going to divide by 2. And when you do that math, you should get 0.0159, and this is moles of oxygen. We will need this in a minute. Okay, I'm trying to find volume, so I have to keep doing some more math. Okay. We have to address the pressure. It tells us in the problem that the total pressure inside the container is 745, but that's the total pressure. It's the pressure of the gas, and it's the pressure of some of the water. We also are going to have to convert moles into liters to solve the problem. Also realize that we're not at standard temperature and pressure, but we will be using the ideal gas law because of this. So the pressure in the question is the total pressure. We have to subtract the water vapor pressure from the total pressure so we can get just the pressure of oxygen. So I will be passing out a chart that has a bunch of pressure values for you. So we look at the table, which I'm passing out to you, and you're looking at the evaporated pressure of water at 23 degrees Celsius. That says that it is 21 mmHg. That's for water. Okay, so we need to subtract our original total pressure minus the 21 from there. And now my pressure of just my gas is going to be 724 millimeters of mercury. So that's the number we're using to finish out this problem. So again, I would rather use atmospheres. So if I'm trying to get to atmospheres, I can just divide this by 760 mmHg, which gives me 0.953 atm. Now I have enough information to plug it into my ideal gas law formula. Okay, so I'm looking for volume, which means pressure equals nRT. Oops, messed up a second. Volume, so it looks like that. Okay, N We solved for it earlier. It's of oxygen, so 0159 moles. R, since this is ATM, is going to be, why is that not on here? Oh, there it is. So 0.0821. Excuse me. And then we're also multiplying that by the temperature, which was 296 Kelvin. All of that's going to be over the total pressure, which was 0.953. So when I do that math, I should be able to solve for volume. Excuse me. And I got 0.405 liters of O2. That is my final answer. Okay, so you have a few practice problems on your guided practice on this notes page. Go ahead and work on those and any work from last class. Bye, guys.